Hey kids, time to do some related rates. Related rates often gives students a hard time, but it's not the calculus. It's getting to the calculus. So for related rates, what this really means is you are solving word problems. So the issue with the word problem is figuring out, do you have related rates? So what you're looking for in the words is you're looking for something that is changing over time. Something or things that are changing and is time in the situation. Then, once you realize what those somethings are, for us, the somethings are going to be a geometry shape. And I'll tell you the most common. The most common geometry shapes are triangles that are used in related rates. The situation involves a triangle, a car going north and a car going east, and the distance between them changing, right? So for triangles, the math, I think, before calculus, I think, oh, is this involving right? Do I have sides and an angle, or do I have just sides? So do I need right triangle trig, or do I need Pythagoras? None of that is calculus. Or do you have circles or spheres? Circles or spheres, and are you talking about the area or volume? How about squares, rectangles, or cubes, prisms? Oh, that's a terrible box. You get the idea, though. Again, area, whoops, that's supposed to say or. Area or volume. You know all those equations. Also, there is cones and cylinders, right? Volume. So for any of these things, you can reach back into your geometry knowledge and write an equation. Now, AP will give you these volume equations. They don't give you a formula sheet, but they'll give you embed in the problem if it's a cone or a cylinder and you need or a sphere, right? They will give you these formulas. They won't give you, if you happen to have an area of a triangle, an area of a circle, area of a square, or even volume probably of any kind of prism. It's just the area of the base times the height, right? They will give you the area, surface area, or volume of a sphere if you need it. All right, so in all of these problems, we need to focus on the words. Something is changing over time. What is that something? What shape is it? And that shape gives us an equation. And then we will worry about the calculus, because the calculus you already know. The calculus involved in related rates is implicit differentiation, which of course involves the chain rule. So when you are done with the setup, which is all the beginning, recognize what shape, what equation. If you are doing calculus in a related rates problem and you're not doing implicit differentiation with the chain rule, you better go find a way to get that in there. So I'm going to do a problem that involves a sphere. I'm going to do a couple triangle problems, one that involves right triangle trig, and one that involves Pythagoras. And I'm going to do a cone problem. And then I'm going to do, lastly, a problem from your homework packet that involves both of these, a cylinder and a cone. Okay, so we have a packet for you, related rate avalanche. And it's got a whole ton of problems in them, along with the solutions that are in files. You only have to do the odds. The odds are the only ones that we're going to collect or make you do, but I'm going to give you tons of practice sites. And of course, you can do the evens, the even problems in there if you want more practice. All right, let's get started. You ready? Let's go. First, I just want you to practice setup. So for these two problems, we are not going to solve anything. This is setup. Okay, so here there is not like I have a, the volume of a sphere or even this cone down here. They're just asking you to write the equations. So radius of sphere, volume of sphere. Find an equation that relates. Relates means equals, right? Find an equation that relates the rate of change of the volume with the rate of change of the time, of the radius with respect to time. So your job is to look at the two things that they gave you, make an equation with V and R in them, volume of a sphere. I will give this to you, and so will AP. You don't have to memorize this one. There is your equation. It is just a geometry equation. You need to get calculus into there. Take the derivative with respect to time of the left side. Take the derivative with respect to time of the right side. So the left side just looks like dv dt. Check. Equals related to, take the derivative of this expression. Now remember, 4/3 is a constant. Pi is a constant. A constant is multiplying stuff to the third power. So imagine, what if I had asked you for 16r cubed. If you wanted to take the derivative of that with respect to r, you would bring down the 3, multiply times the 16, r squared. But what if I'm not asking you to take the derivative of this with respect to r, I'm asking you to do it with respect to t. That's the chain rule. So you are going to bring down the 3, multiply it times 4/3 pi, copy over r, reduce the exponent by 1, but then multiply times the derivative of r. Notice that the 3's cancel out. And you are left with the rate of change of the volume with respect to time is 4 times area, pi r squared, times how fast the radius is changing. Wait, what? Pretty cool, right? So, but I've done everything they want me to do. I have found an equation, dv dt, that relates, equal sign means relates, to rates. The next one asked me to make an equation that relates 3 rates. So let's see what shape. What are the things that they're asking me? The radius and height of a cone, volume of the cone. So again, this equation would be given to you. Volume of a cone is the volume of a cylinder, pi r the area, right? The area of the base times the height, but shrunk by a factor of a third because you've got this space here. If you're instead of going up the height, you have missing space here instead of solid space. To get calculus in there, you are going to take the derivative with respect to time. Related rates, it is the rate things change per time. Notice that I have constants, right? 1/3 in pi is a constant. But I have two functions, and those two functions are being multiplied together. What do you have to do when you're taking the derivative of two functions that are being multiplied together? Oh! Yes, you do have to do the product rule. It never goes away. So the left side is just dv dt. Let's keep the constant on the outside here. And let's just work with the product rule. And what do I have? The first function, r squared, times the derivative of h to the first. Bring down the 1, copy over the h to the 0, times the derivative of h with respect to time. There's really an h to the 0 in front, a 1h to the 0 in front of that. Plus the second function h times the derivative of r squared. Bring down the 2, copy over the r, subtract 1 from the exponent, so there's a 1 here. Spit out the derivative of the stuff. That's it, right? I mean, I could clean it up a little bit, distribute that 1/3 pi through if you really wanted to, but notice that they asked me to relate, which is an equation. Here's my relate, and they wanted, look at my green boxes, r, h, and v. They wanted the derivative of r, the derivative of h, and the derivative of v, all in the same equation. So notice that what this says is the rate of change of volume of this cone. Is it filled with water? Is it filled with coffee? Is it filled with sand? Is it filled with gravel? Is it filled with gasoline? Who knows? But the rate of change of the volume depends upon, right, the rate of change in the height and the rate of change of the radius. Crazy. All right, let's do a problem. You ready? So these were two we didn't do anything. We just set up, we practiced making an equation. That is the important part. Get the equation, do some calculus. That's the vast amount of your points. It's just that usually you're given a problem like this and you're like, okay. So, job. What do I have? What is changing per time? What are they asking me? So let's organize. I recognize this is a related rates problem because of this. I have a radius. It's changing at an instantaneous rate per time. Then they are asking how fast, which is a time issue, is the volume of the bubble changing, when, which is also a time situation. The radius is 10 centimeters because as you can imagine, that bubble blowing, right? It starts out small, and then as air is blown in, the radius and the volume both increase, right? I want to know what the volume is at the instant the radius is 10 centimeters. Okay, so that's how I recognize. So stepwise, I said in the first video, recognize you have related rates. Time is part of the question. Now let's organize our thoughts. Bam. Okay, here's what I want to know. Here's what I want to put down. I'm sorry. The rate I know. So somewhere in the problem, they're giving you a rate of change. Do you see it? Yes. Right? The rate I know is the rate of what? The radius. So write down the rate you know. And units, I write my units down here and I'm organizing and I make note to myself, they've given me units, I have to put units on my answer. What's the rate they want me to find? How fast? Okay, here's my given. Then how fast is the rate I want to find? What do I want to find? How fast what is happening? Changing per time, what? Yeah, volume. That's what I want to find. Put a box around the two variables, R and V, and say, how can I make an equation that relates R and V of a sphere? Again, inside the AP will give you this formula, but come on, you pretty much should know it, right? Here's another thinking step. The replace stuff refers to how many variables you have. So that's why I asked you to put a box around these. If you put a box around R and V, put a box around R and V in your relate equation. Do you have any extra variables? Right? If you have an extra variable and you don't have a rate that you're given or known to match up, you're going to have to do a replace step. So oftentimes, and for the first, 3 examples, we're not going to have to do this. Everything matches up. I don't need to replace any of my variables because I have a box around R and V, a box around R and V, and everything else is just a number. Now I'm ready for calculus. Differentiate with respect to time. There's no time in this equation. You need to bring time into the situation, and you bring time into the situation by taking the derivative with respect to time of the left side and the derivative with respect to time of the right side. That takes the chain rule because the variable R does not match the variable that you are taking the derivative with respect to. So you need to spit out, right? This is spitting out the derivative of the inside. Now, go back to the original problem, go back to the words. When did they ask? Something in the words is given. When do they want to know about the rate of change? So I'm just now, there's my 10 centimeters, there's my given rate, right? You have one equation with 3 unknowns up here. Rate of change of the volume, radius, rate of change of the radius. You took one equation with 3 unknowns and you replaced with 2 givens. I don't usually carry along my units inside my calculations, but I wanted you to see that they do work out. You're putting in 10 centimeters, but you're squaring. So you have centimeter square here. You have 0.1 centimeters per second. So you end up with cubic centimeters per second, which you should because you have volume. So at the instant when the radius is 10 centimeters, the volume is changing at 40 pi cubic centimeters per second, given that the radius is changing at 0.1. Now, if you think about what we did with differentials where we approximated, hey, if the radius of some, right, I did like a Coke can, right? If the radius of the Coke can changes from 10 to 10.1, what's the approximate change in the radius? That's an approximation. This is not an approximation. At the instance when, given the 0.1 centimeters per second, at the instant the radius is 10 centimeters, the volume is changing at exactly 40 pi cubic centimeters per second. You don't have to write it out in a sentence unless somebody asks you, okay, and says, explain what's going on or whatever. I do, right? The word growing or increasing goes with the positive. Right? Those were kind of assumed things. So again, this is an exact answer. With differentials, the purpose of differentials was to approximate. Wasn't changing over time. We are getting an instantaneous change per time. All right, let's do some more. Okay, so again, the challenge with these that students always have with this, especially in a test situation, is you're already pressed about test, right? I mean, about time, and then you're looking at, oh, how ironic, time and related rates of all time. Right, you've got all these words to deal with. You're like, just give me the problem and I'll do it. No, you have to figure out the words and what the words are trying to get you to do. So a hot air balloon is rising. So the first thing I did, right, this picture wasn't there. Here's what I did. A hot air balloon is rising straight up. I drew this first. Straight up, meaning right angle. I'm already thinking, as soon as I drew those two things, I'm already thinking right triangle trig or Sakatoa. Right triangle, sides, Pythagoras, angles, Sakatoa. It's being tracked by a rangefinder 500 feet. So I drew that. There's a side of the triangle. At the moment, there's time. At the moment the elevation angle is, and you know this is a math book because nobody says pi over 4 radians, right? I mean, we have to deal with radians all the time in math, especially because radians is so nice, it's unitless, but we don't talk, right, in normal life about rising pi over 4 radians, whatever. So I'm starting to think, oh, I have a side and an angle, Sakatoa. So at the moment the angle is pi over 4, the angle is increasing at a rate of 0.14 radians per minute. How fast is the balloon rising at that moment? So those are all the words that jump out at me. What do I know? Right? First step, I know that d theta dt is equal to 0.14 radians per minute. That's the rate I know. What are they trying to get me to find? How fast? Okay, rate I know, rate I'm trying to find. Put a box around your variables. Relate. What equation relates the angle of a right triangle and one of the sides? Specifically, the opposite side to the adjacent side. Tangent of that angle is equal to the opposite over adjacent. Sakatoa. Now you don't have to get theta by itself, but I did. I'm sorry, h by itself, because I knew I was trying to find dh dt. So there was my h. So I just made an equation with h by itself so that when I did the differentiation, the left side would be dh dt, what I'm trying to find. Now it's time to differentiate. Take the derivative of both sides with respect to t. 500 is a constant times tangent of a variable that does not match time, so you're going to need the chain rule. Left side is just dh dt. 500 is just the constant times the function, so the derivative is 500 times the derivative of tangent, which is secant squared of the stuff. Spit out the derivative of the stuff. Check to make sure. Did you had an equation that related? Do you now have the rate that you're trying to find and the rate that you're given? Time to replace. I'm sorry, time to substitute. I kind of skipped over the replace step, mentioning the replace step, because remember here, under relate is replace. It's kind of a question. Do I have to replace? And I look at my boxes, theta and h, and the equation that I have here has both h and theta in it. Check, check. So I didn't need to replace. That's why I went straight to differentiation, and now I'm going to substitute. When do I want to know? That was pi over 4, and when the angle was pi over 4. So substitute in dH dt was an equation with 3 unknowns, dH dt, theta, and d theta dt. I knew d theta dt. I know the angle at that moment that they want, and I'm solving for dH dt. And yes, you do have to know that the secant of pi over 4 is the reciprocal of the cosine of pi over 4, which is 1 over root 2. So reciprocate that to get 2, root 2, sorry, square it, get 2. 500 times 2 is 500 times 0.14 is, this, yes, could be on a non-calculator question. Those numbers turn out very nicely. Most of these problems are calculator active once you get down to this point. All right. And notice my rate ended up positive. My balloon is rising. I feel pretty good about myself. Let's do another one. Again, the drawing wasn't there. I made the drawing. So I have a police car approaching right angle. I think to myself, right triangle from the north. So I pick a point and I drive straight down from the north and think right triangle. Then I have another car that has turned the corner, is now moving east. So I drew a straight line right to the east. I labeled them X and Y, but I don't have to. I could have named this P for police car and S for speeding car. When the cop car is 0.6 miles, so when is time, right? There's my time. The police can determine that the distance between them, there's my hypotenuse, is increasing at a rate. There's a given rate. And if the cop car, oh, hey, I've got another rate. At the instant of measurement, what is the speed of the car? So that's what they want me to find. So what do I know? What am I trying to find? Then I've got to relate those two things. Think if I have to replace, then I'm going to differentiate. So what I know, given my drawing where I called the sides X, Y, and Z, I know, right? The radar determined that the distance between them was increasing at 20 miles per hour. That's a rate. But I had another rate, didn't I? They told me that the police car was going at 60 miles per hour. Where's this negative coming from? Yeah, right? Going down. What am I trying to find then? I have 3 sides of a triangle. What am I trying to find? Trying to find how fast. The car is going. So I'm trying to find that rate. Now relate. I have 3 sides of a triangle, X, Y, and Z. What is an equation that you can write that relates those? Whoops, sorry. X squared plus Y squared is equal to Z squared, right? Hello, Pythagoras, thanks. Now, look at my boxes. Do I need to replace, right? Because in here is always a question. Do I need to replace before I differentiate? And that's a question. And that question is answered by this situation. I have 3 boxes with an X, Y, and Z in it. X, Y, and Z. I don't need to replace. Everybody matches up. I have 3 boxes there. I have 3 equations in my relation step, and they all match up. So I can go right to differentiation. Now, don't forget, you are differentiating with respect to time, right? Excuse me, I'm sorry. Bring down the 2. Copy over the x, subtract 1 from the exponent, spit out the derivative of the inside. Do the same thing. Right? Took the derivative of this side with respect to t, and the derivative of a sum is just the sum of the derivatives, and took the derivative of this side with respect to t. And notice I got 3 rates out, which is okay because I was given 2 and trying to find 1. Before I differentiate, I think I'll actually do that. I'm sorry, not before I differentiate, before I do any substituting. That's a z, and that's a t. After differentiating, I say, when do they want to know this, right? Here's my when. When the cop car is 0.6 miles north, who goes with north, X, Y, or Z? And when the car is 0.8, who is 0.8, X, Y, or Z? Cool. So I'm going to be plugging in for X, 0.8. dx dt is what I'm trying to find. I'm going to put in for y, 0.6. dy dt is something I know. And I know dz dt. Oh, uh-oh. Where do I get z from? Yeah, who's there? Oh, Pythagoras. Yeah, come on in. Come on in. Right? Here's a right triangle where you have 2 sides. One is 0.6, one is 0.8. Now, this is really a negative, right? If I've made the rate of change negative to show going down here, right? The speed is 60, but velocity is negative. Well, then this is negative as well, right? So notice that if you forgot all about the negatives, it's not going to matter. I certainly don't care about the negative here on 0.6 because I'm squaring it. So who cares if it's negative or not? So now let's go substitute everybody that we have. dx dt is who I'm after. So in for x, I'm going to put 0.8. Don't know dx dt because that's what I'm trying to find. Plus y, which is negative 0.6, times dy dt, which is negative 60. And again, that's why, right, negatives, I'm going to multiply that together and get a positive. Here's z, whatever that number is, and dz dt is 20. So I'm going to have to move this number over, subtract this, and then divide everybody by 0.8. And when I was done, I got Should I get a positive or negative, do you think? What should I get? Yes, should get a positive, right? Wouldn't that make sense? Right, think about that. That distance is increasing, right? Right. This car's distance is increasing, going to the right and increasing. And when I was done with all that, I got, where can I write this? 70 miles per hour. So if you don't want to think about inside the problem doing your math or who's positive and who's negative, you can kind of, as long as you've set it up right, when you get to the end, you can say like, oh, whatever this thing was should be decreasing. So either write out in words, the radius is decreasing, the speed, you know, right, the card is right, going to the left or whatever you want. You don't have to worry about carrying it along in your math, but you can if you want. So notice that so far I have done we did a sphere problem with the soap bubble. I did a right triangle with Sakatoa with the balloon rising. And now with these cop cars, I've done a right triangle where I needed Pythagoras. Oh, I had a spot for my answer there. All right, let's go to the cone. All right, so take a moment. Look at that. Water runs into a conical tank at a rate of. That's what I know. They're giving me a rate. The tank points down, has a height of 10 feet and a base radius of 5. So it's giving me some dimensions here. How fast is what I want to know. When the water is 6 feet deep. So let's organize. No, 9 cubic feet per minute. What is that a rate of? Volume. How fast is the water level rising? Look at the drawing. What does the water level go with? Put a box around your variables. And your shape. Write an equation that relates the volume and the height of a cone. Now, we've never had to deal with this before. I have a V and I have an H. Do you see what's the issue is? Oh no, that's too many variables, right? I only have 2 boxes, a V and an H. But when I look at my equation, I've got a V and an H, but I've got another variable. No! 3 variables, but only 2 rates, right? One I have to find and one I know. No, this is terrible. This problem is where I have to do the replace stuff, and it all comes from matching my boxes. This R is a dagger. Fortunately, I took geometry and I didn't pay attention all the time, but I paid attention at some triangle work. Now, I don't expect you to really remember this, but now that I've shown it to you and I said you need to remember it, please make sure to make a note of this. There is a triangle with a right triangle with 2 sides. One side is a 5 and one side is a 10. There is a right angle there and the vertex angle there. There is a second triangle that has a smaller radius and a smaller height. However, it also has a right angle and the same vertex angle. From geometry, it was proven that if two triangles have two equal angles. They are not, you cannot prove them congruent, but they are similar, and similar triangles have their sides in proportion. That's how I'm going to replace a variable. Now, there's lots of different ways this might happen to happen. This is the situation that AP is going to test you on replacing. It's going to be with the cone problem, and you're going to need to know this relationship. So it is a little bit of a dagger, but this is the angle-angle similarity relationship. As long as you know that, you can replace that R. Since these two triangles are similar, you can write the equation. Oh, let me change. Sorry, I didn't know why I did blue. That the side of the big triangle to the height of the big triangle is in proportion with the side of the small triangle and the height of the small triangle. Since I want to find dh dt, I want to find dh dt, I want to get rid of r. So solve this equation for r. And replace. Volume is 1/3 pi r squared times h. So that is actually equal to pi over 3, no, 2 is squared, which gives me 4, so pi over 12 h cubed. Now look what I have. Volume and height related, and I knew dv dt and was trying to find dh dt. Now I can differentiate. And think about when. So differentiate this equation, bring down the 3. Copy over the h, subtract 1 from the exponent, spit out the derivative of the inside. So I end up with dv dt is equal to pi over 4 h squared dh dt when the water is 6 feet deep. So I'm trying to find dv dt. So put 6 in here. Put 9 there. And you're solving for dh dt. So 9 is equal to pi over 4 6 squared times dh dt. So dh dt is equal to 9 times 4 over pi times 36. And I got out of that units. What am I trying to find? dh dt should be cubic? No, should be linear. Please make sure, since you're rounding, either you leave pi in your answer, which is totally fine, Totally fine to leave pi in your answer. Exact answers are always accepted. If you use your calculator and round, you must put 3 places past the decimal. You can put more, but you can't put less if you round. All right. So lastly, I did a sphere, 2 triangles, and a cone problem. So the last one I'm going to do is number 17 in your homework packet, in the related rates avalanche packet, because it's a pretty famous problem. The coffee filter and coffee pot problem. Right? Notice when they're drawing it that you've got 2 things going on. You have a cone and a cylinder. So that's why they like this problem. No, we don't want purple. I want yellow. All right. Not a whole lot of words for a lot of things going on over here. Coffee is draining, so going out from a cone into a cylinder. Hey, I've got 2 geometry shapes. And it is draining at a rate of, what is this? Cubic inches means what? Volume. How fast? There's my what I want to find. How fast is the level in the pot? What shape is the pot? Right? The pot is the cylinder. When the coffee in the cone is 5 inches deep. So, what do I want to know? What do I know? Volume, because I'm cubed. What do I want to find? How fast is the level in the pot? So level, height, or you can call it L if you want. What do I want to find? How can I relate with a geometry equation V and H of a cylinder? Area of the base times the height, not shrunk by a third. That's the cone. So, do I need to replace? Do your boxes match? I have a match. I don't need to replace, right? I don't have, oh, wait, no. Uh-oh. Wait, I have an R. Oh, this is terrible. But the replace step I did was with the cone, and this is with the cylinder. Wait a second. Remember, all you need for related rates, I just need to have boxes to indicate what's changing over time. What's true about the radius, no matter what your level of coffee is in the pot. Do you see that? What doesn't change as the water level rises? What does not change? Height does change over time. Volume does change over time. As long as you're in a cylinder, what doesn't change over time? R. So back over here, no, I didn't have a cone, so I don't have to replace a variable. But what's true is I'm allowed to replace with a constant that doesn't change over time. In a cylinder, the radius doesn't change. What is the radius of the cylinder? 6? 6? No, 3. So I am going to replace R, but not with that angle-angle similarity nonsense. I am going to replace 3 squared is 9. So 9 pi h. Now differentiate. Because now my boxes match. Okay, so the cone problem, I had to do a replace, but I had to replace it in terms of the variable I wanted to stay, which was h. Here, because I have a cylinder, I did have to replace, but I was allowed to replace with a constant. But please always be very careful about putting in a constant before calculus. It can only be with something that does not change over time, right? I can't do that in a cone because the radius and the height change over time, but not in a cylinder. So differentiating, I get dv dt is equal to 9 pi is just a constant. Bring down the 1, h to the 0, which is just 1, dh dt. Now substitute in. What do I know? I know the 10. So I'm going to replace here. And I'm trying to solve for dh dt. So dh dt be careful with, if you're going to put this into your calculator, I can't tell you how many times kids make a mistake on their calculator and they type 10 divided by 9 pi, but that means your calculator, who is following the order of operations, does 10 divided by 9 and then multiplies that answer times pi. So either leave your exact answer or make sure on your calculator that you put parentheses around this denominator. What are my units on this, by the way? Are they cubic or are they linear? It's height, right? So it's linear. And what are my units? Inches. So inches per minute. Now, part B says, how fast, so that's what I want to find, is the level in the cone falling at that same moment? Well, what do I know? Notice up here when they talked about the coffee draining from the cone into a cylinder, and they asked how fast is the level in the pot rising when the coffee in the cone is. The relationship between the draining into the pot and the pot filling up, right? The volumes are this rate of change of the volume is the same. Except the rate of change in the coffee pot is increasing, but how about the cone? Falling. What am I trying to find? How fast is the level in the cone? So I am again trying to find height, but not height in a cylinder. What is the equation that relates volume and height of a cylinder? Hopefully this is now old news. You have your factor of a third pi r squared h. So I'm putting boxes in here with my v and my h. Oh no, you cannot put the radius in. You do have to replace, but not with a constant like you did with the cylinder. The radius changes over time, but do you remember what we, whoops, sorry. I don't know why I put dVdt and wasn't doing calculus yet, silly. Right? I have to replace the r, but I can't replace it with a constant because the radius changes, right? As soon as the water level rises, I have a different radius each time. So I need to replace, but what were we going to do? It's our angle similarity situation. So remember we took out and we said, oh, well, we went over here and we said the big radius, what's the big radius of the largest triangle here? Not 6. 3 is to the height, as those smaller radii are to the smaller height. Once again, isn't this nice? I ended up with 1/2 h. So my replacement step, once again, I'm going to put in h over 2 here, so I'm going to get h cubed, but don't forget the denominator is squared and multiplied times this 3. Whoops. Pi over 12 r cubed. Now I can differentiate because my boxes match. Bring down the 3, it's going to cancel with that 12 and make pi over 4. Copy over the r, subtract 1 from the exponent, spit out the derivative of r. So I'm going to put in -9 here. I'm sorry, -10 here. Running out of space, huh? You know what? Maybe I'll erase this over here. So what I know is -10. When at that moment, what was that moment? I forget. Ah, this is supposed to be an H. Sorry, I'm ahead of myself. I was like, wait, what happened? I replaced the R, not the H, silly. So -10 pi over 4 h squared at that moment. What was the H? I forget. 5. 5 squared dH dt. So that's 25 over 4. So I'm going to reciprocate and everything, and I'm going to end up with -8 after I cancel. -8 divided by 5 pi. dH dt. Whoops, then that's, again, inches per minute. Does it make sense that the rate of change of the height is negative here, but is positive here? Does that make sense? Right? As the height is going down in the cone, the height is going up in the cylinder, and they are related. So the height of the cone and the cylinder and the rate of change of volume, right, are all related with this problem. That's why AP likes this one. There are those assumptions that you do have to make. Crazy, right? Now, the last thing before you go, I want to make sure to highlight. Remember at the very first where I was just asking you to set up the equation. I can do this problem a different way with, right? Do you remember when we set up the volume is equal to 1/3 pi r squared h, and we just did the product rule with this, right? Remember with our angle-angle similarity, we got that r is equal to 1/2 h in both of those equations. Well, you know what? Remember when we ended up doing this problem, when we differentiated this problem, we ended up with a dv dt, a dr dt, and a dH dt. Now remember here, we are looking for dH dt. We were given dv dt. We had to replace so that we didn't have to deal with a dr dt. But look, if you really wanted a dr dt, you could do it, right? Can't I take the derivative of this equation with respect to time? And then I get dr dt is just equal to what? 1/2, bring down the 1, h to the 0, dH dt. So I could do that, right? I would be able to replace after I did the product rule. It's just the replacing before eliminates you having to do the product rule when you take the derivative. Kind of crazy, right? So again, what you want to do is lots and lots of practice with these. So we have provided on our website, on our Canvas site, we have GeoGebra applets, Khan Academy practice, right, where you can work through these problems and practice setting them up. The calculus all does tend to be the same. Differentiate with respect to time, which means your implicit chain rule, plug in, okay? Have a swell time. I'll see you at our next live session. Bye, kids.